Hey everybody. So I just didn't like the way that we ended class today. It was kind of like an awkward point. We didn't really get a chance to go further with z-scores. I could tell that some of you were catching on, but I could tell also some of you weren't. And so I wanted to take a minute, probably several minutes, to kind of talk about z-scores since we won't see each other tomorrow. Just FYI, the rest of the stuff that we're going to cover related to box plots and the five-number summary, those aren't too difficult in terms of density, so I think we'll be able to cover those Thursday, and then we can talk about whether or not we still want to have the test on Monday. But we'll go from there. So z-scores is a big deal, something that we're going to use a lot. So what I'd like to do is just kind of go through a couple of examples, kind of give you some takeaways, and then hopefully if you have any questions, anything, you'll let me know, and that'll set us up better for Thursday. So here I just have a couple of the examples pulled from different places. This is one off the sheet that I gave you today. And the examples that I've picked are going to be different ways to kind of use the z-score, and then I'll have a slide where you can see kind of takeaways. So with this case, this is me trying to get at what standard deviation, what z-score is in terms of using the standard deviation. So why, what is one of the useful ways that z-score helps us? So in this case, if I'm looking at someone who, this is a weightlifting thing, if I'm looking at someone that can lift 370 pounds, to me that, I don't really know if that's a lot. There's a lot of factors in that. Like what's doing the lifting? What age group is it? Are they male or female? A lot of things kind of play into whether or not 370 is a lot of weight. If you give me the mean, 310, okay, well, I know that 370 is 60 more pounds than the mean, but I don't really know if it's a lot, right? So this is what I meant by the standard deviation providing scale for us. And one of the ways we do that is by using the standard deviation in a z-score. So the z-score formula that we got is x minus x bar over our s. And what this formula is going to do is we'll say that it's basically standardizing the value that we're finding the z-score of. And what I mean by standardizing it is that it's putting it in the units of standard deviation. It's putting it in standard deviation units. It's not going to be in pounds anymore. So it's not going to be 60 pounds above. It's going to be in numbers of standard deviation. So by definition, the z-score is going to be the number of standard deviations something is above or below the mean. So for this one, we can calculate the z-score of 370, and it's very common to kind of subscript this, especially if you're doing multiple ones. And so I'm going to do 370 minus the 310. I already know that that's 60 pounds above, right? I know that's 60 pounds above, positive number. And then I'm going to standardize it with my standard deviation of 25. So what this is going to do is it's going to put us in terms, or in units of standard deviations. And some quick calculation, I believe that's 2.4. So what does that mean? It means that whoever this person is can lift 2.4 standard deviations over the average. Now, once again, is that a lot? Well, the only thing we really have to look at right now is the empirical rule. And if you look on the empirical rule, something being over 2 standard deviations above the mean is pretty far away. Actually, once you get past about 1.5 standard deviations, especially if you know that the distribution is normal, that's going to be pretty far. So in this case, 370 is a lot of weight. So this person, it doesn't mean that that no one lifts more. It just means that this person lifts a lot more than most people. There's not that much percentage of people that are above this person. Okay, so that's one of the ways we'll kind of look at z-score, is to kind of give us scale, context, and again, this one just kind of illustrating the idea of z-score being a number of standard deviations away from the mean. And again, this one's positive, so therefore above. The next one will be kind of like the one we did with Kathy and Bob. It gives us ways to compare across distributions. So take a second to read that while I kind of set this up. I have two different scores here, one for a history class and one for a math class. So I'm going to subscript these with an H and an M. Because, because the tests are obviously on different scales, right? So on the history exam, somebody scored 143 points, so we don't generally think of tests being out of something other than 100, or at least that's not where I generally go to. And so comparing across that with another exam, where you score 47, that sounds bad. But in isolation, right, it's not, you don't really know whether or not those scores are good because you need to know how everybody else did. And so the easiest way to kind of compare them is with a z-score if you have the standard deviations. Now, again, on both of these, note that you don't know the distribution. So you do not have to know that the distribution is normal in order to compute a z-score or to make this comparison. So for the history class, right, it looks like someone scored 143. The mean of that distribution was 135, right? So pretty easy to note that that's 8 units above. Okay, once again, is 8 a lot? The standard deviation was 5. So that's 8/5 is 1 3/5, right? So 1.6. And then for the math test, we've got 47 minus the mean, which is 39, right, which is 8 units above. So same distance above the average, right? But the standard deviation of this one was 3. So I have 3/8, which is going to be 2.33, right? Am I doing that right? No, 2.67. And so clearly the math exam was, or I say clearly, hopefully it's clear that the math exam score was much better because it's it's over 2.5 standard deviations away, which is really, really far. The person did well on the history exam. They scored over 1.5 standard deviations away at 1.6, but that's nowhere near compared to 2.67. So using the z-score to make comparisons across distributions is a really useful way of using the standard deviation. So there's another example of looking at that. The last one, this is the one we kind of rushed out on. So the point of this was to kind of make connections between comparing different people in the same distribution, but also kind of using the formula itself. And there's a couple of different ways. I think that Emma kind of did the arithmetic in her head, which she was like, Arturo's score will be 12 units above. And I was asking at the end of class where she got the 12. And that comes from the 1.5 of what a standard deviation is worth. But I'm going to show you the formula way of doing that as well. Either way is fine. I'm just going to give you the formula in case the number is a little more complicated. So again, with this, I don't know the distribution. So I don't know if it's this distribution or if it's this like skewed right or if it's normal. It doesn't matter. That's not, we're not looking at percentages of other people right now. We're just trying to compare two people's. So the only thing that I know is that I have an average of 70, which is here. I know that my standard deviation is 8. And all I know right now is that Arturo's score is a 75. So let's start with that. I see this other information, but let's start with Arturo. So if one standard deviation is here, which is 78, and 2 standard deviations is here, which is at 86, right? 8 times 2 is 16, 70 plus 16 is 86. Arturo's at 75, so I know where Arturo fits, right? He looks like he's just a little over half here. And so I can mark that if we want to. So let's see, half would be 74, so 75 would just be here. So here's where Arturo is. Arturo's z-score, right, we can compute. So let's see, we have Arturo, which is 75. 75 minus 70 is 5 over the standard deviation of 8, which I believe we said was 0.6 something. Yeah, 0.6, let's call it 0.63. Now, the other thing is, if I gave you Bella's score, we really wouldn't need a z-score because they're on the same distribution, right? They're taking the same exam. So we wouldn't need a z-score to compare within the same distribution if I have their scores. So that's kind of the twist on this problem, is that you're given the standard deviation of Bella's score in comparison to Arturo's score. And so therefore we kind of have to use a little bit more than just saying, okay, who did better? In this case, we're asking what Bella's score is. So there's several ways to approach this problem. So again, if we think, Emma, I hope you're okay with me referencing you. You were saying this at the end. You said Bella's score is 12 points higher than Arturo's. And I said, where'd you get the 12? Well, if a standard deviation is 8, then 1.5 standard deviations, right? 1.5 standard deviations is 12, right? And you can just plug in an 8 right there. And so 1.5 S's is 12. Now, again, where I initially thought we were going was that Bella's score was 1.5 standard deviations above the mean, which means Bella's z-score would be 1.5, but that's not what the problem says. The problem says Bella's score is 1.5 standard deviations above Arturo's. So if you want to go this route for now, that's fine. We do know that Bella's score is 12 points above Arturo's, so we know that 75 plus 12 is going to be an 87. So that's what Bella scored. But if the numbers were a little more complicated, I don't necessarily know you'd be able to do that in your head, nor would you want to. So for example, if the standard deviation was like 1.78 and Bella's score is 1.885 standard deviations above Arturo's, you're not going to want to do that kind of arithmetic in your head, or at least I wouldn't. And so let me show you another way that we can do this. So I know that the comparison of Arturo and Bella's scores in terms of standard deviations, right? We know that it's 1.5 standard deviations above. So if I take Bella's z-score is supposed to be Arturo's plus 1.5. Well, we already know Arturo's is 0.6, it's 0.625 if it matters. Plus 1.5, right? And that should give us 2.125. Did I do that? I hope I did that right. 2.125. Yeah, 2.125. So we know what Bella's z-score is at 2.125. How can we use this to find what the how can we use this to find the 87? So again, let's go back to the z-score. So I'm going to have to clear out some stuff. Hang on just a second. Let me figure out where all that work went. Okay, so here's the work back. So if I know that the z-score of Bella is 2.125, and I know the z-score formula is x minus x bar, which we already know is 70, over the standard deviation, which we already know is 8. Right, then I just have a little arithmetic here to do in solving for x. So if I multiply both sides by 8, right, I'll get x minus 70 equals 17. And then you add 70 to both sides, right, and you'll get back that x is 87. So, I wanted to give you an example where you were kind of using the information, but you weren't just plugging it in. So, either way of thinking about it, if you're able to shortcut it and figure out how many points Bella is above Arturo, that's fine. Again, I just wanted to give you a way to kind of play with z-score and the formulas in a different way. The last thing I guess I want to say is I want to take this back to the empirical rule. Z-scores are going to play a big role for us when we're looking at a normal distribution. So oftentimes it's easier to talk about probability, percentages, where things are in a distribution without having to worry about the context, because in some context the variable and the values of those variables can be very precise, It can be, long decimals or, whatever. And so we want to have a way to kind of talk about that without having to consider the context every time. And sometimes we do, we won't worry about the context. It won't get in our way, but sometimes it's kind of a pain. And so if you're looking back at the empirical rule, we can think about these hash marks, the inflection values, as whole integer valued z-scores. So if we start right here at the mean, if we think about the mean as being, if we think about the z-score as being the distance that a value is from the mean, then the mean is got a z-score of 0 because it is a 0 distance from the mean. Whereas the z-score of this first hash mark will be 1, z-score of the second hash mark will be 2, and the z-score of the third hash mark will be 3. Over here we'll have -1, -2, and -3, and those are a whole lot easier to deal with and talk about in terms of where things are situated in a distribution than saying, the first inflection value is 793.72, right? That's hard to kind of deal with in our head, and so a lot of times we'll strip the context, standardize it, put it in terms of z-scores, and then we have some easy numbers to play with. So if we take this to like this example that was on the sheet that I gave you on Monday, I believe, these questions can be reworded. So it says, assume the heights of males are normally distributed. So again, we should draw our normal curve with a mean of 68 and a standard deviation of 2.5. What percent of males are taller than 73 inches? So if you take a look at 73, if you're drawing this on the curve, you'll notice that 73 ends up being the second hash mark, right? If you take one jump of standard deviation of 2.5, that takes you to 70.5. Do it again, you'll land at 73. So this question could be worded. It could say, what percent of males have, again, forgive the terrible writing with a mouse, have a z-score over 2, right? Because the z-score of 73 is 2, and so we could just replace that question in terms of thinking about it in terms of a z-score. The same can be done with this one. What percent of males are shorter than 65.5? If you do some quick arithmetic, 65.5 is going to land at one hash mark below. So instead of the question being worded as what percent of males are shorter than 65.5 inches, you could reword this and say what percent of males, I'm not going to write all that again, but have a z-score of less than -1. Right? So we could reword those questions in terms of z-scores instead of the contextual version of the question where we're talking about the height in inches. And again, I know you're going like, why in the world would we want to do that? It's going to become useful later, so I'm just trying to introduce it now so we get accustomed to working back and forth between the context and working with z-scores. I wanted to give you some quick takeaways here. So the first thing is to know the definition of a z-score. It's the number of standard deviations something is away from the mean. So that's hardcore, know what that is. The second, it gives us a way to compare across distributions, especially if you have things that are on different scales, different distributions. It's a nice, easy way to make comparisons across distributions with minimal work. And then the third one is that it's a useful way for us to think about values in a distribution without having to worry about the context. So again, with the last example, you can strip away that context and not have to worry about inches of heights, right? And I know that's something that we're pretty comfortable with, but what if it's a variable that we're not? And so we kind of want to strip it away and then just think about it in terms of z-scores because those are much easier to think about, right? It's unitless, right? I mean, it's numbers of standard deviations, but the number itself is unitless. And the hash marks, those inflection values, are very nice values of 1, 2, and 3, -1, -2, and -3. So I hope this helps. What I'd like to say is, like, just for homework for Thursday, is I'd like for you to take a look at the test that's in D2L. So if you go to D2L and look on the left-hand side, it says materials for test or something like that. There is an old exam that you can take a look at, and I'd like just kind of get your thoughts on where you feel you're at with all that. If we're prepared to take an exam on stuff like that for Monday, or if we need to wait. But other than that, just make sure you're working on the rest of the worksheets that I gave you. If you have any questions, text me, email me, throw up a flare. I'll take the questions any way that I can get them. You got anything, let me know, and I will see you on Thursday.